written in this write-up. You know what I mean?
Okay. Well, without further ado, let's focus on either this one or that one. All right. So welcome to our seminar series at the School of Computer Science. So this week we are very happy to have Untitled Hawk to give a presentation about his research. Untitled is a new faculty at our school, and he graduated from Purdue University in 2015, and he did his postdoc, I believe, at the Northeastern University in Boston. Yeah. Right. So his research interest in the intersection of network systems and security, and the goal is the aid development of secure network systems. And his current project focuses on creating automated analysis tools to discover bugs and vulnerabilities in the networked systems, including real implementations, network protocols, and the Internet of Things systems. So let's welcome Untitled to.
Thank you, Jason. Thank you for the introduction. I guess you guys can hear me, right? Okay. So thank you, everyone, for making time for my talk today. Today I'll talk about detecting bugs in network protocol implementations. So we'll start with a bit information that Jason already mentioned about me. I graduated from Purdue, and then I was at Northeastern for a postdoc, and I joined FIU from this fall. So I basically work in network system security, where currently my primary focus is on building tools for detecting flaws in protocol code. So for this talk today, I decided that I will start with I will start with an overview of my research, and then followed by that I will talk about two of the systems that we built. Okay, so let's start. So we all know building secure systems is difficult, right? And it even applies to network systems or protocols, right? And as a result, we have seen like every now and then reports of bugs and vulnerabilities in the news, right? Let's see one of these bugs. So I'm sure you have heard about this OpenSSL Heartbleed, right? So it is actually a bug inside the TLS keep alive feature. So we'll see how it works. So in the TLS, that's an extension keep alive feature. So what happens is that the client periodically sends a heartbeat message to the server saying that, hey, this is as a heartbeat message that, okay, heartbeat. So, okay, it's so it sends an arbitrary string and also the length of the string. So what the server does as a response just echoes the string. So now let's say the server is running the buggy implementation. Okay. Yeah. And let's say the attacker comes and then sends a heartbeat message with an empty string but lies about the length. So what will happen that the server will send back a string of the same size that the attacker mentioned, and this string is actually coming from the attacker's memory. The server's memory. So sometimes this string can include some private keys as well that is loaded on the memory when server was doing the TLS operation. So this bug talks about, or this bug actually shows that it can leak leak information from the victim's memory, and which can be exploited by an attacker to break the confidentiality of the protocol, right? When it was discovered, it was found that about more than 1 million of websites are vulnerable with this or affected with this vulnerability. So if we take a closer look at this bug, it's essentially a buffer overread vulnerability. It violates the well-defined language standards, right? And it is low-level and protocol agnostic. So therefore, you can defend or this kind of bugs using some kind of memory protection or memory detection technique. Now let's take a look at a code snippet. Okay, can you spot the problem here? You see, there is two back-to-back goto fail. The second goto fail is not actually under the if block, right? So because of that goto fail, this important function never gets called. So, which actually it's required for this function to call this function. But, and finally, if something is wrong in that function, it should return an error. But because of that goto fail, it always returns everything is good, right? So this was implemented in Apple's TLS implementation, so which is also known as Apple's goto fail, right? So this in TLS, that TLS protocol utilizes certificate, digital certificate, to authenticate that a public key belongs to a certain entity, and TLS libraries often provide an implementation for this validation logic. So now, if there is a bug like the one that we've seen, it can lead to impersonation attacks as well as man-in-the-middle attacks. And millions of users were affected when it was discovered back in 2014. So, now if we take a closer look here, the goto fail, right? It's not violating anything at the language level, right? But it's violating something that the specification of the protocol, the function, what it's supposed to do at a high level. So definitely it's not a low-level type bug. This bug is affecting the high-level functionality of the piece of code or the protocol implementation. And it is also specific to the protocol. So therefore, if we apply some protocol agnostic techniques to defend it, we cannot defend these kind of bugs for that. And also, if you notice that if you use some kind of like fuzzing techniques that people use a lot for finding security problems, those will not be even helpful because they don't have any observable error effects, for example, crash. So now you can ask like, okay, what about we test this code utilizing some test cases that will ensure that we have full code coverage, right? It turns out that it's even difficult to generate those such test cases for a large code base like the TLS protocols. And also, even if we have these kind of test cases or this technique might not be useful for other specification bugs. For example, one in OpenSSL CCS injection. So specification defines that the TLS specification defines that how the messages needs to be exchanged during the handshake phase. So that means that, let's say the client, this is a sequence in which the client wants to the client must accept these packets if they are received in this particular order, and this is specified in the specification. So that means that if these messages are received in out of order, client should not accept it. But what happens in this implementation, that even if they are received in out of order, client accepts this message, which is obviously a violation of the specification, but it turns out that it can be deadly. An attacker can exploit this vulnerability to break the confidentiality. Similarly, another bug in called Telnet server, that is the implementation for IoT devices. So their RFC says that they typically they typically have a stripped down version of this implementation. So they implemented that server so that they only handle only one client at a time. So that was their specification says that only one client at a time. So that means that, okay, when the server is connected with one client, it should not accept any new clients. But it turns out that yes, even if a new client comes, the server accepts the new client and starts talking to that client. So that's obviously a violation. But when we reproduce this bug, we found that, okay, attacker can utilize this vulnerability to leak information from the server. So as you can see, all these bugs, they are unique in their own way, right? And we can summarize this notion by this quote, is that every happy families are alike, but unhappy families are unhappy in their own way. So happy families here, I refer to it as a bug-free code, secure systems. They don't have any problems, whereas unactive families are specification-related bugs, that they have a problem, but that's completely different from the other one. Yeah.
So in your previous comments, you sort of draw the distinction between protocol agnostic and protocol specific kind of violations. Do they sort of have a specific meaning that the approach they are going to take, or because, for example, the two examples you're giving now are very specific to that protocol. It's just not being sort of implemented according to the protocol specification.
Yes.
And so are there sort of established methods just to check the protocol implementation to be correct, or the state transition?
Yeah. So I'm getting there, and you are also getting there.
Let me ask you something too. Well, what do you do you suppose that some of these are just extending the protocol rather than violating the protocol? And would that be like a source of?
What do you mean? Oh, okay.
Yeah, like someone, the protocol might say, well, don't accept more than one client, but somebody's implementing it and they say, well, I kind of want more than one client.
The reason was actually Telnet can accept multiple clients at the same time, but they made it for one client, and that's how their data structure is maintained. That they thought that there will be only one client. That's why they didn't separate, distinguish between the data structure. But when multiple clients are connected, they are utilizing the same buffer. So that's the problem. If you are doing it, then you have to do it the right way, right? So that was like for this particular case, this is the problem, right? If they want to extend or do something, yes, they can feel free to do it, but they have to deal with the specification, or they have to make sure they are not violating the specification.
Was it like a should, not a shall in the
That particular, the specification that only one client, it's not actually inside the Telnet specification. It's in their documentation of the code that they want to only support only one client at a time. But Telnet specifies that you can have multiple clients. That's totally fine. But they want to build a stripped down version, a bare bone implementation, but they did not have that checking that if there is ongoing connection, they should not allow any more connection. So that actually lead to that attack. Okay. So yeah, like all the bugs, they have their own problems, but they have one common feature, and that is they violate their respective specifications, right? So now let's generalize the problem. That will answer your question as well. So implementing a network protocol starts with looking at the specification, which oftentimes lists the number of requirements, or in other words, properties, right? Then designer comes up with the design, which goes through the coding phase, and once it is ready, it is shipped for deployment. Okay.
I think this is probably the resolution or something that it's trying to recognize.
I don't know. I'm just mirroring. I don't know. Okay, but prior to shipping, you need to make sure that it is actually the implementation actually compliant with this specification. If all the requirements or properties are satisfied, we can say they are compliant, and if not, then that can lead to non-compliance, which can cause functionality loss, incorrect operational behavior, and sometimes it can have security consequences. So then the question is that what can be done, right? So obviously we can write secure code, which has and also make sure that we are writing these are like formally verified code. Next, we can do that. We can build tools to find bugs and vulnerabilities prior to deployment. Bugs and vulnerabilities in those code before we deploy those implementations. And later, after deployment, we can apply some runtime monitoring technique to make sure that these codes, the implementation that we deployed, are doing what they are supposed to do. So in our research, we primarily focus on creating techniques for automated tools, which are applied in three different directions. One is to detecting specification-related bugs, and then to find manipulation attacks, and also this is to enforce protocol-compliant execution during runtime. So the higher level goal here is to achieve higher assurance on code, right? So just in case you are wondering like what is a manipulation attack, so these are the attacks where an attacker exploit the victim's gullibility to subvert the protocol. So this is also somewhat related to the protocol specifications. But for today's talk, I'll just focus on the detect specification bugs. So our solution, I consider our solution is more like the Captain Planet because we combine concepts and techniques from different areas. So now, okay, let's take a look at that. What are the challenges, additional challenges in this domain? So code complexity, we need to deal with code complexity because events, in a network events determine the execution of the execution flow of the implementation. Second, obviously when we're talking about specification, but unfortunately the specifications, they are not formal. They're mostly written in natural languages like, for example, English. And finally, when we are dealing with this code, there we have to think about the execution paths, and there can be exponential number of execution paths. What is?
Yeah, try changing your resolution. That's a good idea.
Let me check. Yeah. This. There are two resolutions.
That's it.
Better. Let's see. Okay. So there can be exponential number of execution paths because events can occur in arbitrary temporal orders. So when we are analyzing code, we have to also think about those possibilities. So in detecting specification bug direction, we have two systems so far. One is CHIRON and SymCerts, which I will talk about. And in finding manipulation attacks, we have three systems that we build. One, this is related to distributed system. This is for wireless network. And this is for TCP congestion control, which just recently got published. We just got accepted notification last month. So for this talk, I'll just focus on these two systems. So before that, I would like to thank my collaborators on these projects. We're from Purdue, University of Iowa, and Northeastern. So, okay, let's move on to the systems that I want to talk about. One is CHIRON and then SymCerts. So CHIRON is a non-compliance detection tool that we built for stateful network protocol implementations. So the problem statement goes as follows, that given an event-driven protocol implementation P, how can we check whether P violates the desired temporal properties? And can we detect the underlying specification-related bugs there? Okay. So we observe a few things about this network protocol implementations is that stateful network protocol are often, the operation of stateful protocols are often described using finite state machines. So here is a sample state machine, sample or a hypothetical protocol. It says that the protocol starts at the readiest state. Whenever it receives a request, it will send a response and then goes to the waiting state, and it will stay there until it receives an ACK, right? We also notice that the implementation, the developers try to implement this code. When they try to implement this code, they try to closely follow these specifications. Here you can see in the code snippet. And we also notice that specification-related bugs often occur in this kind of code segment where the dev protocol tries to handle network events, or in other words, network event handlers. So in this example, you can see that even after receiving an ACK, the specification says it should return back to the ready state, but the code is not doing that, right? So that's a non-compliance, and the statement that incorrect assignment to the state variable, that's the bug there. So now, how can we detect this kind of issues there? So at a high, CHIRON works as follows at a high level, that given a protocol source code, it will extract the protocol FSM from the source, and then given the desired properties, which are derived from the manually derived from the specification. We feed these properties and the FSM to a model checker, which checks that whether this FSM satisfies these properties or not. If there is a violation, it will provide you a counterexample. And now the question is that this counterexample can be false positive because we are doing some kind of abstraction, right, from the code to the FSM. So that can introduce some false positive. So for that, we do some validation of this counterexample to rule out false positive. And once we find that this the counterexample exists in the code, only then we report about those cases. So now the question can be like, okay, why is it difficult extracting FSM from a code? Isn't it?
We can sort of not use the full screen mode.
Okay. Well, let me see. This one.
Yeah, I think that's everything.
Okay. Let's see. Let me get rid of this. Okay. So you can see that we have two FSMs of the same protocol. One is derived from the specification, and the other is derived from extracted from the from an implementation. So this is manually derived from the specification, and this is we extracted using our tool. So as you can see that both have the same number of states, but the extracted one has a way more transitions. And this is what is actually implemented in the code. So if we want to analyze the code, we need to deal with this FSM, not this FSM, right? And obviously by looking at this, if we want to manually extract this, that will be error prone and time consuming, right?
Just
Yeah.
curious, how do you extract? I mean, how do you extract that?
Yeah. So we apply symbolic execution, which I will talk about next. Yeah. So we apply, yeah.
Can I also ask, if you can just move back on yeah. So why do you have multiple transitions between states? I mean, why are those not represented as a single transition?
This one like very abstract, but in the code level, let's say you have multiple if conditions. If all are satisfied, then you will make a transition to something, right? So if you're not, or there might be some other cases that are, for example, like if you are not satisfied, okay.
So you're saying there's a different label on each one of those
Yeah.
transitions?
These are different labels, definitely, and
That-
there are
that
multiple
none
if conditions.
obviously correspond to the abstract label in the specification.
Yes. And it also depends on this transition, depends on how your code is implemented, right? You may have different types of conditions that you are checking. And if all are satisfied, then you move on to something. If not, for every condition that are not satisfied, you have to have a transition. Okay. So our technique, we use program analysis technique, that's symbolic execution. But before that, talk about our technique, I'd like to tell you briefly how symbolic execution works. Right? Let's say we want to symbolically execute this function, and before that, we will just see that how many possible execution paths are there for this function. Let's say after executing this function, after the first statement, we reach the conditional statement. There are two possibilities: either the branch will be true or it will be false. Let's say after taking the false branch, the function will return, and then after the true branch, we will reach another conditional statement, and again two possibilities: one can be false, another can be true, and on the true branch we reach the assert failure. So this is the possible execution paths for this function. In other words, this is the execution tree for this function. Now I'll show you like how does symbolic execution work. So for symbolic execution, the goal is to explore this execution tree, right? And while doing so, it wants to use symbolic values for the inputs rather than using some kind of concrete values. And while during the exploration, it also keeps track of the variables. Like for example, after the first statement, z is twice b, and it's like z is equal to twice b. And this A, B, they can take any value, so that's why they're calling it symbolic values. So during the exploration, the goal is to also identify the condition, the satisfying condition for each of these branch. So let's say for this branch, it will be converted this condition. And then for this branch, we'll see that you could come from here, and then if you have to go there, it has to be like this, like for this condition needs to be false. So this becomes ultimately the path constraint for this execution path. So by definition, path constraint is that a conjunction of all the feasible branch conditions on input variables. So while doing so, the rest, symbolic vision will just explore the rest of the tree and try to find the satisfying conditions for those paths or the constraint for each of these paths. So now here you notice another thing, that during the exploration, it will fork at every branch statement if both the branches are feasible. So that is one aspect that I want you to remember, because we will need this thing in the 2 slides.
How do you deal with loops in that case?
Yeah. For loop, no, that's fine actually. I see like you were going a couple of slides ahead, but that's really fine. No, for loops, I mean, just to answer that thing, that for this case, we do the de facto approach that people use in this domain, that they unroll the loop for a couple of times. Like instead of looping for a long, I mean, if the loop condition depends on a symbolic variable, it will never end. So that's why you unroll the loop for a couple of times and then execute that way.
Oh, so this is actually dynamically do this
You can do it in symbolic, statically actually. Right. When you are whenever you are preparing the code, you can unroll the loop at that point of time.
But how do you get it converge? I mean, okay.
No, you mean like how do I converge?
Because every time you will update some of these branches, and so it depends on how many how many iterations you get into it.
If your loop somehow depends on the, depends on, like, okay, in other sense you are, I would say like, it is right that, yeah, we have some dynamic stuff inside, even though it's technically static analysis, but we apply some dynamic things, like decide during the runtime that, okay, we can stop the loop and then move on to the next portion of the execution path. Right. So this is a high-level idea for our FSM extractor, that we simulate the execution of the protocol using symbolic execution. While doing so, we want to collect the program state information. So program state is that where you have the values of all the variables that part of the program, and also the PC, that's the program counter, and the path constraint, as we have seen in the previous slide, along each execution path. So for this program state, then we extract the protocol state, so which is essentially a projection on the state variables. So we just collect those values of those variables, which actually gives us the protocol state, FSM state. And from the path constraint, we extract the transition from each of these FSM states. So I used to have an animation to show like how the extraction works, but for the time constraint, I will not go into the detail there. But anyway, so we have to deal with the scalability issue that once Jason mentioned, is that one of the cases, like if we have loop, it will go on. And also a loop is essentially a branching condition. And as we have seen, that forking can happen at every branch statement. So that can lead to path explosion problem, right? And which is definitely a major obstacle for applying symbolic execution for large code base like protocol implementations. So to deal with that, we came up with the protocol state-aware path exploration technique. So we overcome this problem by only exploring paths that are rooted in the newly discovered protocol FSM states. So I'll not go into the detail of this for the time constraint. I'll just, if you're interested, you can look at the paper. So So now after the extraction of the FSM, we need to verify properties, right? So as I said that we look at the properties, we derive the properties from the specifications. Here is an example. You can see the verbose nature of this property. So what it says in a simple word that after receiving 2 back-to-back ISE command, then the receiver must consume the second ISE command as regulated. This is a property actually taken from the telnet protocol. So once we have this property, we translate it in a logical formula, and then we feed the extracted FSM and the property to the model checker to see whether the FSM violates this property or not. If there is a violation, it will give us a counterexample. If not, it will say no counterexample is found. So now, this counterexample essentially tells us that there is a non-compliance, right? And that this and now you can say, okay, what if these counterexamples are false or wrong? Which is possible because we are anyway abstracting from the code, creating a state, which is while doing the extraction, we apply some kind of abstraction like unrolling the loop, right? So because of that, we apply some two-step validation techniques to rule out false positives. Again, I will not go into the detail, so that you can take a look at the paper for that. So the reported, like once we find that, okay, this counterexample actually exists in the code, we report those counterexample to the developer, which essentially shows the buggy execution path, which developer can utilize these counterexamples to reproduce this non-compliance. So we implemented this tool on top of CLI symbolic execution engine, and we also use the new assembly for the model checker. And we applied this tool on several implementations of different protocols, and mostly they were built for IoT systems or IoT operating systems. So we found 11 bugs when we compared, when we applied against 18 properties. So I'll show you one bug as an example. So this was in the IoT telnet server that I even showed at the beginning. So the bug says that the bug is about like accepting multiple client connections simultaneously, whereas the property says that the server should not accept any more new connection when there is an ongoing client. So based on the counterexample, when we look at the code, we've seen that yes, whenever it receives a new connection, it just accepts the new connection. There is no check that whether there is any existing connection or not, right? And the implication when we reproduce this bug, we saw that, okay, it can be utilized by or exploited by an adversary to leak information from the server. So, yeah. Now that we talked about CHIRON, we'll talk about SymCerts. Before that, if you have any question on this.
So,
Yeah.
what does the counterexample look like? I mean, what does it give you? Will it give you, if you go to this particular path?
A trace of the FSM or a path of the FSM. So that essentially says that you start with an FSM state and what events and what are the conditions that needs to be satisfied to move on to another state. And then based on that, you will keep on going, and maybe let's say at it can violate, it can reach to a state that you don't, that according to the property is not valid, or it can do some action while moving from one state to another, which is not valid according to the property.
Does that include like timing information? Because a lot of protocols that rely on time. You know, taking for the example that it's different arrival, the ordering of the messages.
So you're right. So for one case, I mean, it can depend. But in most of the cases, it's most about the order or the temporal order rather than the specific time, right? So that we can reproduce using a symbolic timer, right? Or whether timeout happens or not, that we can reproduce just like using a symbolic variable that will specify. In one case, timeout occurs. In another case, timeout doesn't occur. So you will have both the transitions in that case. Okay, let's move on to SymCerts. So This is another tool that we developed that was particularly looking at with the goal of detecting non-compliance in X509 certificate validation code. So X509 TLS has long been used in TLS. So you have heard about digital certificates, right? So certificates in TLS during handshake, certificates plays an important role. What is, essentially it is used for authentication. What it does is that during the TLS handshake, when a server presents a certificate to the user, which actually helps to user or the client to authenticate that server has the public key, or this public key actually belongs to the server, this public key will be used to distribute the session keys for that TLS session. And as a result, all these keys will be used to ultimately provide the confidentiality and integrity for this session. So X509, this public key infrastructure, these are actually implements as a chain of trust. So as I said, the server presents this chain of certificates to the client, and client needs to check that whether this chain is trustworthy or not. So now that trust needs to start somewhere. So and typically this is the trusted key store. That your computer has a trusted key store. So where the certificates or the root certificates are stored that your computer trusts. So sometimes it's part of your operating system, or sometimes it's part of the browser. So what the client needs to check that whether these signatures, so this root certificate, if it is root certificate, let's say, why am I using this? Yeah, I can use this. If it is a root certificate, this will sign another certificate of a certificate authority, and this is the server certificate which it receives from that intermediate certificate authority. So this certificate will be signed by this guy, and this certificate will be signed by the root certificate. All the client needs to do is just check whether the signatures are correct or not, right? Now you can ask, like, okay, how hard that could be, right? It turns out that it is one of the most error-prone and complicated code to get things right here. So, and the reason is basically these certificates contains a lot of fields, right? And those fields sometimes can be very confusing. They also have some time-related stuff like expiration dates. Yeah, so you have to, the developer needs to make sure they're not misinterpreting the time. And they do have some optional extensions which if they are used, they need to be used correctly, otherwise there can be some critical consequences. So now let's see that, okay, these are the reasons that things can go wrong. Now, what will happen if things go wrong? What will happen if non-compliance occurs? So there are two contrasting pitfalls. First is that if your certificate is overly permissive, it can lead to some malicious attacks. The adversary can exploit those facts and then launch some attacks. And if your certificate is too much, or not certificate actually, if your implementation is too much restrictive, then it will create some compatibility issue and interoperability issue. So the problem statement goes as follows, that how can we check implementations for of X509 validation logic, which are typically inside the SSL libraries, for compliance. So let's take a look at some insights about certificates. So the input, now imagine the input space for these certificate chains. It's huge, right? But each of these certificate chain, when they are presented to a implementation, right? What can happen? The implementation can either accept it or it can reject it. So now, based on that, if we can input the entire universe of this certificate chain to an implementation, we will get some of the certificate which belong. We will get the. The implementation will split this universe into two parts. One is the accepting universe, and another is rejecting universe, right? So, based on that, we created SymCert. So the high-level approach works as follows: is that given an implementation, instead of giving the entire universe, we created a symbolic certificate. We provide this certificate to the implementation, and we apply symbolic execution there, which provides us ultimately the accepting universe and the rejecting universe, which are essentially some logical formulas, right? So for each implementation, we will get one set of formulas that will represent the accepting universe, and another set of formulas that will represent the rejecting universe. So now let's say, let's say from one library we get this accepting universe and the rejecting universe, which we can check against the RFC to see that whether they are implemented correctly or not. And now let's say we have like multiple other libraries. When we have multiple other libraries, we can do something more than that. Let's say from library 2, we also can get the accepting universe and the rejecting universe. So now once we have that, we can utilize this tool to do some cross-validation. So what do we mean by that? If this library accepts a certificate and this library rejects that certificate, that means someone is doing wrong, right? And that is a non-compliance. That gives us a non-compliance a formula that can represent the non-compliance. We can utilize SMT solver to solve that formula to create a concrete certificate, so that which can be used to reproduce this non-compliance. So again, we have to deal with this scalability issue in symbolic executions. So here, what we do is that when we create the symbolic certificate, we actually mix some concrete values as well for those fields which we know that okay, this will not be changed for any cases, or for some cases if there are some what is that called, is that TLV, if you know that, like oftentimes there are like a variable length data. If there is some variable length, so if we put the length symbolic, then it will keep on ongoing. So we put a fixed length, and then but the content of the list, we put some symbolic variables there. And we also apply some domain-specific optimization. I'll not go into the details of that. For that, you can take a look at the paper. So we applied our tool on 9 different libraries, SSL libraries, and which were actually used for many applications that are developed for IoT platforms. And we found 48 number of non-compliance instances on these libraries. So I'll just briefly give you a few examples here, and these are like related to the time that are used in the certificate for express the expiration date of the certificate. So RFC suggests that the version 3 X509 certificates can only have expiration date that will range from that will have this range from 1950 to 2049. So now when developers implement that, they do some mistakes there. They misinterpret this this requirement or the RFC, and as a result, they do some mistakes in their code. So let's say for Matrix SSL 1, because of the bug, the range of the certificate that they allow is this, 1996 to 2095, and this was the error. This is the implementation of that logic. So because of that, they do have like some severe implications. For example, a certificate that is expired in 1995, if that certificate is presented to this version of the SSL library, it will accept this certificate because it thinks that it will expire in 2095, right? Again, a similar mistake here is that in the Tropic SSL, the range is incorrect, and this is due to the way they implemented their logic. And that also has an implication, like any certificate that is old enough, which is expired in 89, they will accept that certificate as a valid one. And this is a very interesting one, that incorrect range. You can see that it's pretty close, right? 1951 to 2050. And this is the logic that makes this mistake. This is an off by error. You can see that. Just an off by error in their code. And as a result, any certificate in 1950 will be accepted. Even though they were pretty good, they try to maintain the thing, but just because of this equal sign, that will mess things up. So, okay. So we're done with the SymCert. But before I conclude, I'd just like to mention about what we are doing right now. So we are doing some projects in different directions. One in the IoT system security, another in the internet security protocols. We're looking at like TLS and SSH. And also we are doing one project in Bluetooth security. And this is for students. If you want to get involved, you can email me and also take my courses. I'll be teaching CNT 6207, that's a distributed process, and system security in the fall. So, okay, thank you. Thank you for your time. I'll be happy to take questions.
So the way we find the bugs in the implementation, do we do it reverse engineer it and see if there is anything went wrong with this specification?
Yes. There is a huge line of work where they look at or they actually check the specification. So in formal methods area, model checking, previously they used to focus on the design, whether the design is correctly formatted, right? But back then, applying those techniques in implementation was very difficult. So that's why they thought that, okay, this is like an area where people do theoretical stuff. But nowadays that they are seeing some application in the implementation domain as well.
Right. One more question is that because these tools are built on a lot of tooling, on some sort of tool chain, you have the operating system, you have a bunch of libraries that you are using. So when a new update rolls up, you probably just do a kernel update or just the operating system update. So probably you need to update everything, and people just don't update everything, and that's how hackers get into your system. So how do you check in those cases, because they're all different things. You're gonna the way you have some transitions, you're gonna end up more and more transitions when you have these mismatches of the versions of the library.
So you are talking about like vertical security, like you ensure security from the operating system to the application layer and all the libraries.
Yes.
So here we are focusing on like one portion of that entire stack, like okay, this particular protocol, right? So obviously we are assuming that everything below or everything up, the application is like using these libraries properly, or the operating system is correctly implemented, right? That's obviously the focus is here just on that particular protocol. And also it's showing like in other sense, like think about it, just one protocol, that is how difficult it is to work with this protocol. And then in case of operating system, there are like multiple layers, multiple types of libraries. So that will be a huge challenge to work with operating system. And there are people, when they work, they also try to narrow down their focus in some aspects of the operating system.
So
Yeah.
for what was it called, symbolic execution.
Yeah.
You require source code, right?
Yes.
So you have to have source code.
Yeah.
Do you do sort of the executable code
On the binary?
Yeah.
So there are symbolic execution that you can do on the binary as well. But in the one thing is that when you are doing on the code level or the source code level, you have those high-level information. But on the binary, you lose a lot of high-level information, right?
What kind of high level?
For example, if it is a part of the structure, or if it is you are is in a function, you are what is that called? Like if it is a part of the buffer and all this, like what's the name of the buffer? You can get those information there, right?
Yeah,
But in the binary level, everything boils down to your register and then memory location, right? So that becomes difficult to translate. I mean, here is another thing, like you have properties, these are written in English language, and you have code. So, but if you want to check this stuff on the code, either you have to make this, whatever, you abstract the code so that both on the same level, the property and the abstraction, or you can get the property at the code level, or maybe in the middle you get the property, it's somewhere down the line that has like much more, less ambiguity, and you have the abstraction made so that you can scale the entire checking stuff.
So, just one more
Yeah,
question.
yeah.
Okay, so I remember Mark was asking the transition diagram
Mhm.
where you have a lot of lines and
Yeah,
you
yeah, yeah.
say they're because of all this
Mhm.
minute different
Mhm. Checking.
checking. And I didn't get exactly what you do for the mono checking part to ignore those sort of.
No, we don't ignore. We don't ignore actually. So the entire FSM that you see, we feed that as a state machine to the model checker. But those label that we use, the label actually has like the path constraint you have seen, right? So those path constraint will be also feed to the model checker. There actually we do another layer of translation which I haven't talked about, because I feel like always when I talked about CHIRON, it has layers of translation and it takes a lot of time. And then when I'm talking, no, that is also automated. Only the manual part is that the writing the property. Right. That is like we look at the RFC and then figure out, okay, this can be a property that we can check on the FSM. Yeah. But that translation, everything else is automated there.
Any more questions? All right, thank you.
Okay.